Hello everyone, this lecture is exclusively recorded for second year BSc student of BK Birla College, Kalyan. This is mathematics class. In this lecture, we will study second fundamental theorem of integral calculus, and we will also define primitive and or antiderivative along with few examples. So let's start the lecture. So first of all, I will define the primitive or antiderivative definition. So primitive, or it is also called as antiderivative. Let small f is a function from closed interval a comma b to r. If g is a function defined on closed interval a comma b to r is differentiable, then g is said to be primitive or antiderivative of f if g dash x is equal to f of x for all x. So the derivative of g should match with the f of x. So let's have some example. Suppose I have a function f of x as 2x and g of x as x square. So you can see that g is differentiable. Being a polynomial, it is differentiable. So from this we can find out g dash x, which is 2 of x, which matches with the f of x. So this would imply g dash x is equal to fx. This would imply x square is antiderivative or primitive of 2x. Now similarly we can have one more example. So for example, if I take f of x is equal to some cos x and g of x, you can easily guess now it will be sin x. So you can see that derivative of g, being a trigonometric function, it is differentiable. So g dash x is cos x, so g dash is same as fx. So what does this imply? This implies sin x is antiderivative or primitive of cos x. Now one may observe that, is primitive unique? So the answer to this, it's not unique, because if I take example as f of x is equal to some, again, cos x and g of x is some sin x plus some constant c, right, where c is not equal to 0, assume that, so that second and third will be different. Now you can see that the derivative of constant is always 0. Here again g dash x is equal to fx. So sin x plus c is also a primitive of cos x, and similarly sin x is also a primitive of cos x. So we got two primitive for cos x. They are they are sin x plus c and sin x. So this would imply sin x plus c is primitive of cos x. So it's very clear that one may have more than two primitives. So primitives are not unique. So hence primitive is not unique. So they are unique up to the constant, or two primitives differ by a constant, because if I take this, you can see that sin x is also a primitive here, sin x plus c is also a primitive. So they differ by a constant. So this is one of the reasons. So in fact, I will write down the remark. If gx is primitive of fx, then gx plus c is again primitive of course you should remember this, where does the c belongs to R and c is non-zero. C belongs to R and c is not equal to 0. That should be noted. Okay, so in other words, we can see that two primitive differ by a constant. Two primitive differ by a constant. One can easily prove this statement because it's not difficult. So suppose let f has two primitive, say g1 and g2. So these are the two primitive of f. So if g1 is a primitive, what does this imply? g1 dash x is fx. Similarly, g2 is a primitive, so g2 dash, derivative of g2 dash is again fx. So if I subtract this to equality, then I will get g1 dash x minus g2 dash x is equal to 0. So what does this imply? g1x minus g2x derivative, so the dy dx of this is equal to 0 for all x. If the derivative of a function is 0 for every x, then this function has to be constant function, because we have proved this in the semester in the last year with the help of Lagrange's mean value theorem. So this completes that two primitive differ by a constant. g1 and g2 are two primitive, their difference is constant. So we have proved this statement. Now let me prove the second fundamental theorem of integral calculus. So before proving, let me state the statement. So second fundamental theorem of integral calculus. Oh, we will abbreviate is second fundamental theorem of integral calculus. So let's write down the statement. Let f is a function from closed interval a comma b to r, be a Riemann integrable function, be a Riemann integrable function. So, and a function g from closed interval a comma b to r be an antiderivative of f. Then the theorem says that integration a to b f of x dx, this integral is straight away g of b minus g of a. So if we know the antiderivative of f, then integral of f is very simple. It just depends on the endpoints g of b minus g of a. Okay, so let's prove this. So let p equal to x naught, which is equal to a comma x1 comma x2 comma dot 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 xn is equal to b, be any partition of closed interval a comma b. It's given that g is antiderivative of f. So what does it imply? This would imply my g dash x is equal to f of x for every x belongs to open interval a comma b. So when g is antiderivative, this means that g is differentiable. Note that here g is differentiable. So g is differentiable on open interval a comma b. So if the g is differentiable on open interval a comma b, then it will be differentiable on any subset of open interval a comma b. So this would imply g is differentiable on open interval a comma b. But if I take any subinterval, that xi minus 1 comma xi, that is a part of closed interval open interval a comma b. So if the function is differentiable on a larger domain, it will be definitely differentiable on the any subset of that domain. So this would imply g is differentiable on open interval xi minus 1 comma xi for all I goes from 1 to up to n. Why the reason is because xi minus 1 comma xi is a subset of closed interval a comma is a subset of open interval a comma b. Okay. So g is differentiable. Differentiability implies continuity. So g is differentiable and continuity. So we can always apply the Lagrange's mean value theorem. So by Lagrange's mean value theorem, we can say there exists a Ci belongs to open interval xi minus 1 comma xi such that The Lagrange's mean value theorem says that my G dash at Ci is equal to G of Xi minus G of Xi minus 1. You need to recall your first year BSc Lagrange's mean value theorem now, because we say that there we said f of b minus f of a upon b minus a is equal to f dash at c, something like that. So g dash at, we are applying now on g, so g dash at ci is equal to g of xi minus g of xi minus 1 upon xi minus 1. Okay, so what does this imply? I can multiply this xi minus 1 to this side. So let me simplify this. So what I'll get, g of xi minus g of xi minus 1 is equal to g dash at ci xi minus 1. But I know what is gi dash. What is g dash? Because here it is said that g dash and f are same. G dash and f are same. So instead of writing g dash, I will write down small f now. So this would imply g of xi minus g of xi minus 1 is equal to f at ci xi minus 1. So let's call this as some, this is called as 1, so from 1. Now what I'll do, I'll take this summation over it. So if I take summation, I goes from 1 to n, then it will be g of xi minus g of xi minus 1 is equal to summation I goes from 1 to n f at ci xi minus 1. Right. But then we know that what is LHS, because this is telescopic sum, so all the alternate terms will get cancelled. So it will be, I will left with g of xn minus g of x0, but g of xn is b, so g of b minus g of a is equal to summation I goes from 1 to n f at ci xi minus xi minus 1. So let me call this as number 2. This is going to be important for me. Okay, now let me define a few terms. So now define capital Mi as supremum of fx such that x belongs to xi minus 1 comma xi, and small mi is equal to infimum of fx such that x belongs to xi minus 1 comma xi. So it's very clear that f at ci is definitely less than equal to lower bound and the upper bound. Mi is an upper bound. So let me take only this part. So now small mi less than equal to f at ci. This would imply, if I multiply this with xi minus xi minus 1 less than equal to f at ci, then again xi minus 1, and then on next step I will take the summation. So summation I goes from 1 to n small mi into xi minus 1 less than equal to summation I goes from 1 to n f at ci xi minus 1. Now this would imply, now this is my LPF, and this is less than equal to, I know this, what is this term, because number 2 is that only. Number 2 says that it is g of b minus u of a. Now since P is any partition, and if I take the supremum over it, then LPF, supremum of all LPF such that P is any partition, that will be my LF. And this will be, anyway this is number, so here now this is a constant, so it will not change. So it is g of b minus g of a only. So let me call this as number 3. On the same line, we can do it for the, now this remaining part. The remaining part is means basically this part, f at ci less than equal to capital M. Now in that case we will get g of b minus, so uf we will have for the f at ci is less than equal to capital Mi, okay, f at ci. So if I multiply this with xi minus 1 and then take the sigma and all, so then what I will get, I'm not writing now in between step, so I will have g of b minus g of a is less than equal to upf, and if I take infimum over it, then I will have g of b minus g of a is less than equal to uf, right, number 4. But I know f is R integrable, but it is, f is R integrable, it is given. That's a given part. So f is R integrable, what does this imply? This only implies that uf and LF are same, and that is same as the integral a to b f. So from 3 and 4 you can say that uf and LF are same. So what does this imply? So from 3 and 4 we can say that g of b minus g of a is less than equal to LF, which is equal to integral a to b f, which is less than, which is equal to uf, which is less than equal to g of b minus g of a. So this would imply my integral a to b f of x dx is straight away g of b minus g of a. So this completes the second fundamental theorem of integral calculus. Of course, there is another approach to this. So after this, one can have another way also. Let me write down the, or then alternate way one can see is as follows. So we know that f at ci is between small mi to capital Mi. Right. So what does this imply? This would imply, so if I multiply by xi minus 1, and if I take summation over I, this is less than equal to again summation over I f at ci xi minus 1. I goes from 1 to n, that I am not writing now. I hope you will understand that. So xi minus 1. So let's complete this bracket. So this is basically my LPF, and this is less than equal to this. I know by 2 it is g of b minus g of a, and this is nothing but UPF. Okay. Let's call this as some equation number A, inequality number A. And also we know that there is a standard inequality. Also we know that LPF is always less than equal to my LF, which is equal to integral A to B F, which is also same as UF, and UF is also less than equal to UPF. This is number B. Why I could write this? F is R integrable. That is very important fact, I know. So if I subtract B from A, then what I'll get is as follows. So B minus A is so B में से U subtract करना है. So I supposed to multiply A by minus sign, and then I will add with B. So if I multiply A with minus sign, then minus LPF, this will be greater than equal to then this will be minus in bracket G of B minus G of A. So let me write down how does it looks. So B minus A I am doing, right? So here it will be LPF minus, I will have UPF here, less than equal to integral A to B F minus G of B minus G of A, okay, so less than equal to UPF minus LPF, right? So now you can see that here this can be further written as, I can take minus sign outside, and here I can say it is plus, so here it is minus. So this number is lying between this minus to plus. So like we had a rule, one of the rule, if mod x less than equal to a, if and only if x lies between minus a to plus a. So you can see that this number lies between UPF minus LPF minus to plus. So this would imply, I can straight away say that modulus of integral A to B f of x dx minus G of B minus G of A, this number modulus of this must be less than equal to must be less than UPF minus LPF. But what I know, UPF minus F is R integrable. So UPF minus LPF has to be less than epsilon by Riemann criteria. So I got this difference is less than epsilon. So this would imply modulus of A to B fx dx minus G of B minus G of A is less than epsilon, and this modulus is always positive number. So a number is greater than equal to 0 and less than epsilon. This would imply that number must be a 0 then. So A to B. This is one of the nice result of your first year BSc. Minus G of B minus G of A. This number has to be 0. This number is 0. That means you can straight away say that integral A to B f of x dx is equal to G of B minus G of A. So this completes the theorem with another approach. So you can either write down the earlier one or other one after this. This is an alternate method. So from this, the proof has two steps. Like, where is that? Yeah, here you can either take this approach, 3 and 4 approach, or you can take the inequality A and B approach and you can complete. So this completes the second fundamental theorem of integral calculus. Thank you.